So, a couple of things. Today we're going to start our review for the final exam. Most of the material that I'm going to be covering, actually all the material that I'm going to be covering these next 2 days comes directly from that ACS study guide. If you don't have a copy of the ACS study guide and you'd like one, you can walk across the hall over to the chemistry office, and I think they're $22 or $23. You can get your own copy. There should be a copy still on reserve in the library. And I can tell you that those individuals who make use of the study guide and actually work a lot of those practice problems do significantly better on the ACS final. So the review guide has a bunch of problems, it has explanations, it has solutions. It's a great way to study between now and then. It's condensed, which is, everybody get out of breakfast? I see Anna brought hers with her. So anyway, the review, the study guide is well worth the money. You don't have to buy one. You can borrow it over in the library. But again, students who use the study guide typically do significantly better on the ACS final. So it's in your best interest to use that for your study between now and then. The other thing, I will hand back the exams at the end of class today. There were about 4 questions that we had low success rates on, and I'll cover those on Friday so that everybody has had an opportunity to see the solutions for those. And so there was a 3-point offset on the exam that's not on your paper. That will be applied at the end of the semester. So there will be 3 additional points added to this exam. All right, so today we're going to talk a little bit about nomenclature, structure, a little bit about acid-base chemistry, and some stereoisomerism. This is going back to the 255 stuff. So we're going to kind of cover some 255 material today, and then on Friday we'll be getting into more of the 256 stuff that's covered in the study guide. Okay? So you got to know your functional groups. At this point, this should be, this should go without saying, right? You should have a thorough understanding of your functional groups at this point, because on the ACS exam, they assume that you know what an aldehyde, a ketone, an ester, a nitrile, all those functional groups that we learned about, they assume that you know them, and they will use them by name, not just structure, okay? So you need to know your functional groups. So this is a table that we used in 255, right? So we've got alkanes, alkenes, carbon-carbon double bond, alkynes, the aromatic compounds with the aromatic ring, phenyl group. And not only do you need to know your functional groups, but you need to know what you can do to those functional groups, right? Those things should be rolling off your mind right now. You need to remember that alkanes, basically you can oxidize them. They can do free radical chemistry. Alkenes, you can do addition chemistry. Right? We can add things across the carbon-carbon double bond. We can add things across the carbon-carbon triple bond. We can't add things across an aromatic ring, but we can do electrophilic aromatic substitution. As you see these functional groups and you're going through them, the types of reactions that they can undergo need to be rolling off your head. If that's not the case, you really need to buckle down and get that last minute, because that's going to be one of the things that you need to be able to do on these exams. Alkyl halides. Right? What can we do to alkyl halides? Substitution. We can do SN1, we can do SN2, we can convert them to ethers, we can convert them into Grignard reagents. Those types of things need to be rolling off, again, off your head. Alcohols, right? What can we do to them? We can convert them into alkyl halides. We can dehydrate them. We can make ethers from them, right? We can do all those types of things for alcohols. The OH, the H is acidic. It has a pKa of around 16 to 18. Okay? Ethers, what can we do with ethers? Ethers were pretty inert, right? But there was some chemistry that we could do with them. We could cleave them with strong acid, for example, right? We could cleave them with a strong acid and make alkyl halides, for example. Amines, right? What can we do with amines? Well, they can function as nucleophiles. They can function as bases. We can diazetize them. We can do Sandmeyer chemistry with them, right? We can do all that kind of stuff with amines. Thiols, basically same kind of stuff that we can do with alcohols. Sulfides, okay? Those functional groups. And of course, aldehydes, ketones, anything that contains a carbonyl group. I can just tell you right now, the ACS final exam really likes the carbonyl group, right? What do we know about the carbonyl group? Well, we know it has a distinct IR absorption, roughly where? Yeah, somewhere between 1,500 and 2,000, depending on whether it's an aldehyde, a ketone, or an ester. But in that region, that's right. What can we do to aldehydes? We can oxidize them to carboxylic acids. We can do that using a variety of reagents. One of them was the Tollens reagent. One of them was, you can do that with Jones reagent, right? What else can we do? We can do aldol reactions. That's chemistry at the alpha carbon. What else can we do? We can reduce them with things like what? LEH will work, but sodium borohydride will also work in that case, right? So we can reduce them. We can add Grignards to them. We can add alkyl lithiums to them, right? We can convert them into alcohols. We can make carbon-carbon bonds with them either through aldol or Grignard additions to the aldehydes. We can basically do the same thing with ketones, more or less. We just get different products, right? If we reduce an aldehyde, we get what kind of alcohol? We get a primary, and a ketone will give us a secondary, right? So you got to remember those kinds of things, right? But pretty much so we can do the same types of stuff with ketones that we can do with aldehydes. Carboxylic acids, what can we do with the carboxylic acids? Pardon? They can be decarboxylated under certain conditions, right? If they're beta keto acids, for example. What else can we do? We can certainly convert them into other things. We can make acid chlorides from them. And by making acid chlorides, we can convert them into a variety of different functional groups. We can take carboxylic acids and we can convert them into esters, right? So basically, carboxylic acids can be converted into esters, amides, and acid chlorides using a little chemistry, right? All of those things we can do with the carboxylic acid functional group. Ways in which we can make carboxylic acids. Probably the most numerous that we've talked about, right? We can make carboxylic acids by oxidizing alkenes and alkynes. We can make carboxylic acids by reducing benzoic groups. We can reduce carboxylic acids to alcohols. We can make carboxylic acids by the oxidation of alcohols using Jones reagent if the alcohol is a primary alcohol, right? Lots of different ways to make carboxylic acids. We can make them from Grignard reagents, the whole 9 yards. So we learned a lot of things that we can do with carboxylic acids. Probably going to be an important thing on the exam. We learned a lot about it, right? So real quickly, what kind of functional groups do we have in these two molecules? Let's just look at penicillin G to start with. Yeah, we do have a sulfide, right? Very good. What else do we have? We have a carboxylic acid. Do we have an amine? We have an amide. We've got one right here. And then we've got you could think of it as a tertiary amide. That's certainly not incorrect, but it's special here. Why is it special? It's cyclic, and so it's a lactam, and this happens to be a beta-lactam, right? So it turns out that the beta-lactam is the pharmacophore, as we call it, for penicillin. That's what allows it to kill the bacteria. And we talked about that a little bit back in 255, I believe, right? And so penicillin G has all of these different functional groups. Does it have any stereocenters? I haven't drawn them out, but clearly it's got a stereocenter here. It's got a stereocenter here. It's got a stereocenter here, right? So 3 stereocenters in penicillin G as I'm counting them. Ibuprofen, right? Probably what you took after the exam on Monday, right? What kind of functional groups do we have here? Again, we've got a carboxylic acid functional group, and we've got an aromatic ring, and we've got an alkyl chain hanging off of it, right? Okay? And so, again, carboxylic acids being quite important in a variety of not just regular old organic stuff that we do in this type of class, but things that you depend on to get through the day sometimes. All right, let's look at some problems from the ACS study guide. I want to mention you will not see these problems again, but all the problems in the ACS study guide come from retired exams. So it at least gives you an idea of how they're going to examine. And I would argue that the most current version which we use examines in a very similar format. Okay, again, you won't see these questions, but this is how they examine. And it's also very important for you all to remember your good test-taking skills. Before we get into these, what are some good test-taking skills that we need to remember? Get a good night's sleep. That's good. Will that really happen, though? No. It won't, so let's just forget about that one. But it is a good way to prepare. Huh? It's a good idea if you can. And we say it all the time and nobody ever listens to us, so I've just stopped saying it. What else? Yeah, eliminate things that are absolutely incorrect, that you know are incorrect first. That's always a good test-taking skill, right? So if you know something just can't be, I know that a ketone doesn't get reduced with LAH to make a tertiary alcohol. Anything that would be a tertiary alcohol would be wrong, or if it was a primary alcohol, you would immediately know that that had to be wrong, right? This exam is graded, as all exams are, on the number of correct responses. You need to increase your chance of getting correct responses, okay? That's what you need to do. I know it sounds silly, but that's the truth. And you've also got to not let your pride get in the way and sit there and focus on one question so long that you exhaust a lot of energy. If you don't know something within a minute to a minute and a half, you need to move on. You've got 70 questions. If you have no clue within a minute or a minute and a half, put a little asterisk on your answer sheet, not on the actual test booklet, and come back to it later when you have time. But if you get yourself flustered and you get yourself frustrated, that does nothing good for you in all the questions that come later, okay? So yeah, you could struggle through it, spend 30 minutes on a problem and get it right, and then miss the next 20 because you're running out of time. There's no kudos for that, right? There's only points for right answers. So, in the structure shown, the functional groups that are in the triangle, the rectangle, the pentagon, and the circle in that same order are. So what I would do is I would look at the triangle first. And I would ask myself, what's that functional group? What's that functional group? That's an amine. Which ones do not have that? B. So I can eliminate B. Right off the bat, I can eliminate B. This rectangle, what is that? That's an ester, right? So what can I eliminate now? A. So we just eliminated A and B based on that. So we know it has to either be C or D. So even if you didn't remember what the amide and the ether were, which shame on you if you didn't, but if you didn't, you could at least get yourself down to a 50-50 odds. And any gambler will tell you, you put lots of money on the table when you have 50-50 odds, because you're going to come home a winner at the end of the night, okay? That's a good thing. So what's the right answer? It is C. Nomenclature. Need to remember how to name things. At this point, nomenclature is pretty well rolling off of your tongue, as if it's almost a second language to you. If I say pentane, you can immediately see what pentane looks like in your head. I know you can, right? If I say 2-methylpentane, you could probably come up with a structure. Now, I can give you a really long name that wouldn't be the case, right? But the exam keeps it pretty simple. What you need to remember is that there's going to be a prefix, a parent, and a suffix. You need to remember that. The prefix tells us what the substituents are and where they're located, right? The parent tells us the longest carbon chain, the longest continuous carbon chain, and the suffix tells us the functional group. If it's an aldehyde, what will the suffix be? Al, right? If it's an alkane, what will the suffix be? Ane. If it's an alkene? If it's an alkyne? There you go. You got it, right? So those three things got to come together, right? And so this was an example we looked at last semester where we're looking at a molecular structure in what kind of form here? This is condensed. Now, many of you may be able to name a structure from a condensed structure. And if you can, that's fine. There's nothing wrong with that. Personally, I can't do it. I can't look at that and derive a name easily. So I always take a condensed structure and I convert it into a bond line drawing. That's the very first thing that I do. And I would highly recommend that you do it as well. It's a lot easier to name from a bond line drawing, in my opinion, than from a condensed structure. Okay? You will be given scrap paper to write on. I strongly recommend that you use it. There are two things that I've learned by teaching this class over the last 10 years. Students who actually use their scrap paper or their spaces where I say draw here always do better than students that leave that blank. So if you're turning in your ACS standardized exam to me and that scratch paper is blank, you haven't really given it your best effort. That scratch paper should be scribbled on and written on and crossed through and marked a lot. Okay? And so the one thing that I can tell you is that folks who utilize that and work through problems do a whole lot better. All right, so what do we got to do? Find the longest chain, and what is it? It is a hexane chain, and we can either have the green numbering, and if we, or we can have the white numbering, right? We can number left to right or right to left. So we have to figure out which one's correct. If we use the green numbering, we would come up with 3-ethyl 5-methylhexane, and if we use the white numbering, we would come up with 4-ethyl 2-methylhexane. Which one of these is correct? The second one, right? That one right there. Why that one? That's that first point of branching rule, right? Very important, okay? When you look at these names, though, because you will be given names like this on the exam, there's no place for you to actually write the name, right? And so a lot of people will look at something like this and go, well, 3 comes before 4. That's not the rule. The rule is the first point of branching rule, right? Yep. And it's a common mistake. I mean, it does happen, right? Because a lot of times it is, you know, what comes first? Well, it's the same thing here, what comes first, but it's that first point of branching. Which carbon do we have that first point of branching is what comes first, not the numbering. Okay, so don't get those concepts confused. So what is the correct name for this compound? In these types of problems, the very first thing you're going to do is identify what? The longest continuous chain, the parent. And in doing so, what did we come up with? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so no matter how I think about it, 1, 2, 3, 4, 5, 6. Yep, no matter how else I do it, it's 8, right? So given that, what can I eliminate? I can eliminate A and B right off the bat. Knowing the longest chain eliminated 2 of the 4 answers, and I'm at 50-50 odds. Not bad, right? Just by being able to count to 8, all right? So we know it can't be A, we know it can't be B. So we got 1, 2, 3, 4, 5, 6, 7, 8, right? What's the right answer? It is C. It is 2,2,7-trimethyl-octane. D has the right parent, but carbon number 1 isn't a tert-butyl, right? But that looks like a T-butyl group, but it's not a T-butyl group, right? Why is it not? Because it's part of the longest continuous chain. It's only a tert-butyl if it's attached to the longest chain, right? So if we had 20 carbons, where at carbon number 3 there was a T-butyl group, it would be a T-butyl group. It would be tert-butyl, right? But not in this case, because what looks like a T-butyl group is really part of the longest continuous chain, okay? So now, the one thing that you have to remember about alcohols in terms of nomenclature is the OH group is a privileged functional group, and that it's going to take the lowest possible number. So you have to keep that in mind. But you're still going to find the longest continuous chain, but you're going to number such that the OH gets the lowest possible number. So what is the longest possible chain here? 1, 2, 3, 4, 5, 6. Yep. So what can I eliminate? I can eliminate B. I can eliminate A. And I kid you not, going through this stuff, you're going to be able to eliminate half your answers. Were you able to easily eliminate half the answers on my exams? Not so easily. Okay? Go through and eliminate incorrect answers. Okay? So it can either be C, which is 3-methyl-6-heptanol, or it can be D, which is 5-methyl-2-heptanol, which would be correct? D. And the reason, because we want the numbering to give the OH the lowest possible number. Okay? Don't forget about your Lewis structures and your formal charges. Right? We use the circle method to determine formal charge. What does formal charge mean? What is it? The difference between? Yeah, so it's the valence electrons that come in from the periodic table minus the number it formally owns. And in Gen Chem, you learn some stupid equation that makes no sense. I mean, it works, but it's just that. It's what does it come in with in terms of valence electrons and how many does it formally own. You just subtract those two numbers. And if you can draw a circle, you can figure out how many it formally owns. Because the circle, everything that's inside the circle belongs to the atom. So the lone pairs completely belong to that atom. But as it goes through a bond, what does that mean? You split them. That's right. So these two lone pairs, that means those 4 electrons belong to oxygen, but one from this bond and one from this bond belong to oxygen, and the other 2 from those bonds belong to carbon. That's what this is telling us. Oxygen comes in with how many electrons? And it now formally owns? 6 minus 6 is always 0. Right? So you're in good shape there. Okay? So let's look at this problem. In which of the following Lewis structures would the iodine be assigned a formal charge of +2? Now, a problem like this, you need your scratch paper because you can't actually write on the exam because we keep using these exams. So you'd need to draw these out, circle the atoms, and do the math, right? So how many electrons does iodine come in with? 7, right? So if it comes in with 7 and we subtract how many from this one? So would that be right? Nope. So here we've got 7 minus how many? 5. So would that be right? Yeah. B is the right answer. Okay? Now, there are some things that you just need to remember about formal charge. Nitrogen with 3 bonds and its lone pair is what charge? 0. Nitrogen with 4 bonds? +1. Nitrogen with 2 bonds and all of its lone pairs? -1. Oxygen with 2 bonds? 0. Oxygen with 1 bond? -1. Oxygen with 3 bonds? +1. Carbon with 4 bonds? Carbon with 3 bonds? +1 if there are no lone pairs, right? So a carbocation. 3 bonds and a lone pair? Minus. 3 bonds and a single electron? That's a radical and it has a formal charge of 0. That's right. Those need to just come to you. You don't need to be wasting time calculating formal charges on things like nitrogen, oxygen, or, what did I say, nitrogen, oxygen, and carbon. Those should just be coming to you, okay? But if they throw you something like this on like an iodine or some other atom, you're probably going to have to do that because it just hasn't been sunk into your brain as much, right? Question 4 here, what hybrid orbitals are used to form the sigma bond between carbon number 1 and carbon number 2, respectively, in the structure shown? What's the hybridization of carbon number 1? Okay, and what's the hybridization of carbon number 2? So what are the 2 hybrid orbitals that are overlapping? sp2 and sp. That is exactly right. Because carbon has an sp2 orbital that is overlapping with an sp orbital from the C triple bond N. Those are the 2 hybrid orbitals that are overlapping to form that sigma bond. What orbitals between the carbon and nitrogen are used to form the pi bonds? Well, they're not up there. Okay, they're not up there. But what orbitals are between that carbon and that nitrogen, that carbon-nitrogen triple bond, are used to make the pi bonds?
You're talking about that carbon and that nitrogen.
I'm talking about that carbon and that nitrogen. What orbitals are used to form the pi bonds? It's the p orbitals. Remember, they're unhybridized p orbitals, and they form the pi bonds. Okay? So don't forget that. Right? The pi orbitals between these two atoms are not put together by the hybrids. It's the unhybridized p orbitals that remain. Because what does sp mean? It means one s orbital and one p orbital hybridized to make two new orbitals, which means you have to have two p orbitals remaining for that carbon. Okay? Which carbocation is the most stable? It is B. And why is it B? Yeah, so it's tertiary and it is also allylic, right? So if you had to rank these carbocations in order from most stable to least stable, what would be then the next? C. And why C? It's allylic, and resonance trumps substitution, right? So I'd go B, C, then A, and then D, right? And remember, D is unstable because it's on an sp2 hybridized carbon that's part of a carbon-carbon double bond. And so it's not in a p orbital, right? That positive charge would be in an sp2 orbital, which is not terribly stable. Question 8. What factor is responsible for the greater heat of combustion per methylene unit for cyclopropane than the heat of combustion per methylene for cyclohexane? Just see. Remember, you get less heat out total by burning cyclopropane than you do from cyclohexane because there's fewer carbons. But when you correct for the number of methylene units, you find that cyclopropane actually gives you more heat for combusting on a per methylene unit basis. Okay? Question 9. The heat of combustion for neopentane is 3250, and that of pentane is 3269. Which statement best describes the relative stability of these two compounds? Remember, the more heat I get out when I burn something, right? That means it must have been very unstable and it's coming down to a more stable situation. Whereas something that is more stable is already closer to the floor, right? And so it gives us less energy when it burns. If we're talking about isomers, and in fact these two molecules are isomers of one another. They have the same number of carbons, the same number of hydrogens. So they're going to give me the same number of amount of carbon dioxide and water when they burn, but they're not of equal stability. Neopentane is more stable than pentane. Why? Okay, sort of. It's substitution. The more substituted the alkenes or alkanes, the more stable they are, remember? So we want to have more substitutions. Onto which of the onto which of the numbered atoms in the structure can the negative charge be moved by resonance delocalization? So where can I move this negative charge is what they're asking. What do you need to be doing on the exam for a question like this? Drawing resonance structures. So draw some resonance structures for me. Do not try to solve these problems in your head. Breaking your bones there? What's the answer? Pick one. It is actually D. Why can I not do B and C? Draw the resonance structure for me. When I move this negative charge to here to form a carbon-carbon double bond, that moves these electrons onto carbon number 2, not onto carbon number 1. Right? So I can move it to carbon number 2, I can move it to carbon number 4, I can move it to carbon number 6, and I can ultimately move it to carbon number 7. I can never get it onto the oxygen. Okay? Again, arrow pushing, going to be very important. Okay? Question 12. Which of the 4 resonance structures contributes the most to the overall picture of this molecule? It is A. What can we eliminate in a question like that? You can eliminate D, you can eliminate B. Because remember, we want, where possible, we want every atom to have an octet. All of them have charge separation. Okay? So we really don't have to worry about that too much. But we want every atom, where possible, to have an octet. And B and D do not have octets. Okay? Assuming that all are planar, which structure would be considered aromatic? What are the rules for aromaticity? Completely conjugated, cyclic, planar, Huckel's rule, 4n plus 2. Each and every one of those has to be met, right? And they just told you you have to assume all are planar. So you're good. Are all of them cyclic? All right? Are all of them completely conjugated? They are. So what are we trying to figure out? Huckel's rule. 4n plus 2 must equal the number of pi electrons, and n must be what? Whole number. 0, 1, 2, 3, 4, right? So what are you going to do here? You're going to do some math, right? And then when we do the math, what answer do we come up with? We come up with D. D is the only one of those that would be an aromatic molecule. What about if they were to ask anti-aromatic? What changes? 4n equals the number of pi electrons, and A would certainly fall into that. I don't know about the other two or not. I'd have to do the calculation. Okay. But I've seen questions like this before on the old exam. I don't know if those are on the new exam or not, but on the old exam, and again, nowhere on the scratch paper did anybody try to solve that problem. You know, some people, I guess, can do that kind of math in their head pretty easily. I have trouble with it. Counting it all up, keeping track of it in my head. So write things down. Acids and bases, the most important concept you'll leave this class with? Why the sigh? Acids and bases? Right? We are going to stick to the Lewis definition. It's the most useful definition of acid-base theory. We know that a Lewis acid is an electron pair acceptor. We also call those electrophiles. And we know that a Lewis base is going to be an electron pair donor. We also call those nucleophiles. We learned that all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles. Again, an important concept for you to keep in mind. So given that definition, question 1 here asks, which species would best act as a Lewis acid? Let's eliminate first. What can we certainly eliminate? We can certainly eliminate C. And why can we certainly eliminate C? Why not? It's a radical. It is not an electron pair donor, nor is it an electron pair acceptor. It will accept a single electron, but that is not the definition of acidity. Okay, so you can eliminate C. There's one more up there that you can eliminate for sure. You can eliminate A. And why can we eliminate A? It's negatively charged. It's not going to accept a pair of electrons anywhere. Everything has an octet and it has a negative charge. Getting a pair of electrons close to something that's negatively charged, hard to do. All right, so we can eliminate A and we can eliminate C. Now we're down to 50-50. B or D, which one of those would best be a Lewis acid? Why B and not D? All right, we have a weak pi bond. So I can have a pair of electrons from some nucleophile attack this, right? And it would accept them. But I can have a nucleophile attacking this carbon. Is that a good leaving group? So is the nucleophile going to attack it? No, right? So it's all about electron pair accepting, right? Which structure helps explains why the aniline ion, shown here, is a stronger acid than the ammonium ion? Now, looking at all those structures, the very first thing, there should be something that's popping out. What's popping out to you? What's popping out to you about A? Okay, that's certainly true. And what else can you tell me about A? What can you tell me about the nitrogen? It's got too many bonds, doesn't it? It violates the octet rule. Can we violate the octet rule? Nope. So it can't be A. So is C violating the octet rule? It sure is. So we can eliminate that as well. So that comes down to either B or D. Which one is the correct answer? What's the charge on a nitrogen with 4 bonds? +1, right? That's right. So it's that structure. Ah, good old amino acids. If an amino acid is dissolved in water and the pH of the solution is adjusted to 12, which is the predominant species present? Oh, wait, that sounds like an exam question. I just reworded this one. It is D, right? I told you it was 1.5 molar sodium hydroxide, which has a pH of around 12, right? But that's what the structure would be. And I think I said glycine. What is the order of acid strength from strongest to weakest? Which one of those is the strongest acid? 3. You know that right off the bat. 3 is the strongest acid, so I'm going to eliminate what? I'm going to eliminate A and I'm going to eliminate D. Always start there. If you have to guess, 50-50 odds are better than 1 and 4. What's the right answer? It is C. 4 is a stronger acid than 2. Why?
Because the chlorine's on the neighboring carbon.
That's right. So remember, as we fall off, right, the inductive effect falls off pretty quickly. So you need to remember the effects on acidity. Obviously, this is talking about the inductive effect. What other effects did we talk about? The resonance effect,
Element.
the element effect, and the hybridization effect. All of those things you need to refresh your memory on. Which of the following is the strongest base? It is B. Why did you pick B? All right, so this oxygen atom has lone pairs which resonance delocalize into the ring and make this nitrogen more basic, right? Good. Stereoisomerism, you're going to have to remember your stereoisomers. This nice little flow chart comes right out of the ACS study guide. Very important for you to be able to look at a structure and determine whether or not, number one, it's an isomer. Number two, whether or not it's going to be a constitutional isomer or some other type of stereoisomer. And if it's a stereoisomer, you need to be able to tell whether it's an enantiomer or a diastereomer. You're going to have to be able to identify those types of things in this type of exam, on this type of exam. Okay? So again, very nice chart in the study guide. I highly recommend you spend some time looking at it. Okay? So which Newman projection represents the most stable conformation of 3-methyl pentane when viewed down this carbon-2, carbon-3 bond? I will allow you to use a model kit. What do you think? A is the most stable. Look at your model kits. Okay? Basically what you want to do is get this methyl group not to be in between these two large groups like it is here. Okay? So you never want things to be crowded sterically, right?
Can you tell us the difference between A and C?
Between A and C? Yeah, so here the C, so you've rotated basically this front carbon and you've put the methyl group now really close to the larger ethyl group as opposed to closer to the smaller methyl group.